Hi, welcome to the to part two of lecture two for the data path topic. And in this lecture, we will discuss counters and just a quick review of what we have covered in earlier courses, specifically in digital logic. We know that counters consists of in flip-flops. Okay, so these are the flip-flops of counters, and typically we would like to have counters connected in one clock. If they have different clocks, then they are asynchronous counters. But we would like always to work off synchronous counters, so one central clock and those counters so their output goes from q0 all the way to qn minus 1 and the output here typically starts from 0, and then we increment or decrement then all the way to output 1 1 1 1 1, and this is when the output saturates and we go back and repeat the same sequence. So for example, if you have a 3-bit counter, you will count from 0 0 1 0 0, I'm sorry, 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1, and then go back and start again. So this is an up counter. If it is a down counter, so you go from here to here to here to here to here to here to here all the way, and then you come back and repeat the series. The up and down counter basically it depends on how you create your counting sequences. Understand one thing, that the number of counts is equal to 2 to the n, where n equals the number of flip-flops. Okay, with that in mind, let's go back to with this quick review. Let's go back to the lecture here. Of course, before I go back to the lecture, we have this here, the logic, where we update whatever here flip-flop I have, the D or T flip-flop. Of course, in digital logic class, you studied about the T flip-flop and JK flip-flop and D flip-flop. Honestly, nobody uses in practice the T flip-flop and the JK flip-flop. These are just academic flip-flops that are meant to be part of the basic information that you take in digital class. But in practice, nobody uses T flip-flop or J. Very limited use. Everybody uses the D flip-flop, which is easier to design, easier to code. And these are the kind of flip-flops that we have in practice. Okay, so let's go back to the lecture, and we'll see. So here is our first counter here. This is a asynchronous counter, and basically the very first bit, what it does, it flips the output, and typically this is a typical behavior of the least significant bit. Then the output, or the negative of the output of this, which is q0 prime, goes and becomes a clock. And that's why this type of design, we say asynchronous, because the clock of this flip-flop is not triggered by, or the input clock for this flip-flop for q1 is not triggered by clock, rather the q0 prime. And then the q1 prime becomes a clock for the flip-flop here, which is q2, and the q2 prime becomes a clock for the. So this asynchronous design of counters, the purpose of it, if you plot the output of this thing, so let's say, for example, this is the clock. Okay, so see what happens here. Kind of very quick drawing here, not very accurate, but let's just get things going here. So you will see that this is a clock, and you see q0 behaves like so. Here, so it goes like this. Here. Something like this. So this is here. Okay. So what is noticeable here about Q0? It has half of the frequency of the clock. All right. So now, how about Q1? Let's see. Let's get this in a different color here. Q1. Q1 behaves like this. Here like this. So it is the Q1 frequency is half the frequency of Q0. How about Q2? So Q2 will behave something like this. Um, so Q2 here. Okay, I have to check on the edges here if they start at 1 or 0. I'm not, but this is the key thing here. If the frequency of clock is f then the frequency of Q0 is f over 2, and the frequency of Q1 is f over 4, and the frequency of Q2 is f over 8, and the frequency of Q3 is f over 16. Okay, what do you mean by frequency? Well, look at here at the, for instance, let's see, look at here, for example, at the period here, right? At the period of Q2. How many clock period it spanned? Well, it spanned 1, 2, 3, 4, 5, 6, 7, and 8. So eight periods of the clock. So this is what this is Q2, which is what we called, it has a frequency divide by 8. So when we say that Q2 frequency is f over 8, it means that the clock period spans 8 clock. The clock period of Q2 spans or includes 8 clock period of CLK. Okay. Okay, so that is the about the asynchronous counter, which is basically we call it a clock divider and produces different clock frequency. In digital systems, it is quite often that we need to design the system with separate clock frequencies. Okay, so this is one circuit that does that. Okay, now we go to the binary counters, which do up count, up, down, and a fully featured counter with all the reset, load, up and down. Okay, in previous classes, like the digital logic class, we had to design the counter from basic flip-flops, started from the state machine, then the using K-maps, to the end of the story. Again, I have bad news for you. Nobody does that. And the reason is, in practice, we have circuits that we work to extreme optimization. These circuits called adders. Okay, so I use adders to implement counters. So, for example, let's just talk about up counter. You see, here is the adder. Okay, this is the adder here, which is very optimized. And this adder, what it does is it adds. So I can have this carry ripple, I can have this as carry look ahead, I can have this as binary tree, whatever fast adders I have. And then I have a bunch of flip-flops here. Okay, a bunch of flip-flops, which is right here. So they save the output of the adder, and they go to the input. These are typically D flip-flops. They take the output of the adder and save it, and the output of the flip-flops are Q0, Q1, da 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 da. And then what we do in the next cycle, we feed the output of the flip-flops to the adder, and the adder, all it does, it adds one. Where is this one? We'll see this tie to VCC. This is the one. This is a carry one. a carry in of value 1. So this adder, so this adder, what it does, it adds Q's, right, plus 1, right, and it adds this to the input of, or update the input of the flip-flops, and that's why how we will have. If I may take this, so basically Q, which is next, right, equals Q, which is present, okay, present Q, right, plus 1. Okay, so that's how we do it. Well, okay, so this is an up counter. What if I need up down counter? Again, I use an adder. The basic structure here, I use an adder. Okay, so this is my adder, and here are my flip-flops, because the output of the adder are saved in these D flip-flops, and here are my Qs, right? Okay, now understand one thing: in an up-down counter, I have to do that the Q which is next can be Q present, okay, plus 1. This is to do what? This is to do the up count. How about the down count? Well, the down count, the Q next, well, which means the next value of the Qs equals the present value of the Qs minus 1. Okay, how can I implement minus 1? Well, in a 4-bit flip-flop, the minus 1, take the 2's complement for this to get the minus 1. So this is plus 1, minus 1 is by the 2's complement. This is equal 1, 1, 1, 1. Oh, okay. So by adding, let's see, let's go here and pick a color here. One. By adding here, Q present, Q next equal Q present plus 1, 1, 1, 1, which is the 2's complement of minus 1, I can do a down count. Okay, so this counter here, it will do up and down. How do I know this? Well, I use a control signal. This signal, if it is a 1, I'll do a down counter. If it is a 0, I'll do an up counter. So notice when this is a 0, when this signal is a 0, I'll have zeros here. So I'm adding zeros to the Qs, except I will invert the control signal. It becomes a 1 here. So I have a carry in of a 1, which goes and add 1 to the Qs, to the present Q, so that I will have Q plus 1 updating the flip-flop. So the adder will do Q plus 1. Well, what if I have, let's see, what if I have here the down? I need to do a down. So the control signal must be set to a 1. So when I set it to a 1, these values becomes 1, 1, 1, right? And 1 here. So basically, I am adding 1, 1, 1, 1, 1. What about the carry in? Well, the carry in here becomes a 0. So I'm adding 1, 1, 1, 1 to the present value of the Qs. That should do a down count. Beautiful. So now I know how to do the up down counter. How is this what I do all the time with counter, just up and down? No, sometimes I need to do other functions with counters, and this is the most a more advanced counter, as we explain here in this figure. So here is my basic up down counter here, which I just made, which is I just designed. Okay, sometimes I need to add another functionality called preload the counter. Preload the counter. Yeah. Sometimes I need to start counting from different number than 0, 0, 0, 0. Suppose I need to start counting from let's say 0, 1, 0, 0, from 4. So what do I do here? Well, then in this case, I have this mux, right? I have this mux. Let's just use a different color here. I have this mux, which allows me to preload the counter with whatever value I wish. Okay, so this extra mux provide for me the load function. So I have the up the down, the down, the up, which is I already, and the load. How about a reset? Why do I need to reset the counter? Well, sometimes when you start your system and the hardware, when you power up the digital system, you want to bring up the counter to a known value, which is 000, and that's the function of the reset, which is right here. Okay, and we have another function here, which is the enable, and the enable, it stops counting for some reason. Typically, enable functions in digital systems for circuits are associated with saving hardware, meaning when I want to have a part of the digital system to sleep, to lower the power, because I know that part is not required to function at now, so I put enable equals to 0, and that makes the counter or whatever digital systems or the flip-flop sleep. And we will cover this at the end of this course, where when we discuss sequential element, and we will see how we will make them or disable them with an enable function, so those flip-flops do not function to lower the power. Okay, so basically here this enable signal is, if enable equals 1, then we function as normal. Enable equals 0, then this counter does not update itself. The output is constant. It doesn't function. It is as if it is nothing happened in the digital. It will keep its present value, but nothing is being updated, even if we have a clock coming. Okay, all right. So these are the flavors of binary counters that typically we see in VLSI systems. Now, one of the things that we use in digital system is the linear feedback shift registers. Few years back, a group of students were doing a graduation project, and they came to my office and said, we want a piece of hardware which generates random numbers. I said, that's easy. That is your linear feedback shift register. So the linear feedback shift register, what it does is it creates, let me add the word, it creates random number, but let me add the word pseudo random number. Pseudo, what do you mean by pseudo? Well, it's kind of random, because these random numbers, they behave according to a polynomial, mathematical polynomial. And if you know that polynomial, you can predict those numbers, but they act as if they are random, and therefore we call them pseudo random. That's one thing. So they are the output of a mathematical formula. Number two, they are repeated. So we generate them once, and then if we go to the last value, we go back and repeat the same sequence. So while they might look like as random, they are predictable and they are repeatable, and that's why we say pseudo random numbers. Okay. Now, so take a look at, for example, at these group of registers. Typically, linear shift back register consists of a group of registers like so. So we're going to explain the skeleton here, the most important components. So the very first thing you will see, group of registers which are shifted to the I'm going to say to the right. No one is going to oppose if you flip the drawing, but I'm going to say you have a shift register that shifts to the right. Okay, now where the output, so this is D, this is Q, this is D, this is Q, this is D, this is Q. Okay, now, and also what we have here as extra is that this exclusive or implements a mathematical formula, and this exclusive or, typically, the output of it goes to the very first flip-flop. Okay, notice that I'm shifting to this direction. Okay, now the inputs of this flip-flop typically are from designated cues. Those cues they are specific value, and typically they conform to a mathematical formula. Okay, and we will see how. So the most important things, you have a shift register with an exclusive OR where the inputs come from certain queues according to mathematical formula, and the output of this exclusive OR goes to the input of the first flip-flop. Now, take a look here at, let's just see here. Um, uh, uh, let's use here a different color here. Let's say, for example, he says, assume that we have Q0, Q1 equals 1, 1, 1. So you have Q0 equal 1 here, and Q equals 1 and Q equals 1. Notice that these 1 1 are output of this exclusive OR, and then which means that there's a 0 here. So the 0 sits at the input of this flip-flop. Once I have the clock comes after the clock, the first clock, this will change to a 0 because I'm going to shift the 1 here, and this will shift to a 1, stays as it, and this will shift to a 1. Now I have 1 1, so you can see here, see here, this is the output. Q0 changed to 0. Now I have 1 1, which is still a 0. After I shift to the second clock, this becomes a 0, stays as 0. This becomes a 0, and this becomes stays as 1. Okay, so this after the second clock, I will see this. Now I'll have what? Now I'll have a 0 here, which is the output of a 1 becomes. Now after the third clock, this will change to a 1. Okay, and this is 0, and Mm. and this is a 0. So 0 0 1 0 0 1, which is what we have after the third clock, and so on and so forth. And so I keep getting these values, right, until I go to the last value here, and then oops, I'm gonna go back to the initial value, which is 1 1 1 1. Once I get 1 1 1 1, I'm gonna repeat this sequence. Okay, now, so if I take a look at their values, you can see I'm gonna say to Q2, Q1, Q0, so that I tell their value. So this is 1, so this is 1 1 1, and this is 1 1 0 1 1 0, and this one is 1 0 0 1 0 0, and this one is 0 0 1 0 0 1, and this one is 0 1 0 0 1 0, and this one is 1 0 1 1 0 1, and this one is 0 1 1 0 1 1, and this one is 1 1 1. So if I take to the if I may get their values, okay, so this is here, this is here 7, okay, 6, 4, 1 and 2 and 5 and 3 and 7. So these, they look like for me random numbers. And look how we go back and go back to 7, and we repeat the same sequence. Okay, so the other thing that we notice here, since I am having here 3 flip-flops, isn't it uh, 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 reasonable to expect that I'm going to have 2 to 3 codes, which means 8. But this one, if I count those sequence, I'll get 1, 2, 3, 4, 5, just 7 codes. I have just 7 codes here. So the number of codes here, 7. Why not 8? Okay, two points about the length of the sequence. First of all, unless you choose, you must choose carefully the equation. And if you don't choose carefully the equation, sometimes you repeat the sequence after 2 codes or 3 codes. The maximum you can get is 2 to the n minus 1, which is what I got here. 7 is 2 to the 3 minus 1 equals 7. That's the maximum, even if you are the best mathematician and you create this equation. So the question is, why minus 1? Because there is one sequence you cannot use, which is what? Which is 0 0 0. If you have all zeros in these queues, it would the linear feedback shift register will not function. The next value will be 0 0 0 0 0 0 0 0 0. So in the linear feedback shift register, there is one value, one sequence you cannot use, which is 0, 0, 0, because we remove that sequence from the function of the linear feedback shift register. The maximum value I can get is 2 to the n minus 1. Okay, now here's what I just said about these equations. These are the mathematical polynomial, and this implement a mathematical polynomial. Okay, so now how do I translate this mathematical polynomial to hardware? I map the xi maps to qi minus 1, and that q minus 1, its output will go to the XOR. Okay, so notice x3, you will have this q2, its output will go to the XOR. Then x squared maps to q1, its output goes to the exclusive as an input to the exclusive OR. Well, how about q0? Well, do you see x here? No, I don't. Therefore, you don't have this output of q0 goes to the input of the XOR. So the inputs of the XOR really confirm to the what? To the formula. What about this one? Well, this one is really represented as the output goes to as an input to the first flip-flop. Okay, let's take another example here. So here is a polynomial here. Okay, and I need how many flip-flops to create this? I need 8. So x8, watch, q7, input to the XOR, x7, q6, input to the XOR, q6, you see q5, input to the XOR. Okay, x1, q0, input to the XOR. Now understand one thing, that we are numbering the q's from q0 all the way to q7. Okay, and so this is the hardware implementation. Now what's the length of the sequence here if we are careful? Well, we can expect up to 2 to the 8 minus 1, which is 2 to 55 random numbers or pseudo-random numbers from this hardware. Okay, all right. Okay, with this I conclude this lecture, and we'll follow up with the rest of this lecture in the next part. Thank you very much.